Okay, before we start, let me just remind to everybody that is attending that we are recording this meeting as part of our series. So whoever is not comfortable with this, maybe please turn off your camera. Otherwise, everything should be good. Okay. We can maybe start. So welcome everybody to this third apartment of the ELLISxUniReps speaker series. Today, we are very excited to have Victor Veitch from the University of Chicago and Google DeepMind. That will be our keynote talk speaker. And then we're going to have Luigi Gresele from the University of Copenhagen that is going to be our first speaker. Just as a reminder, this meeting is going to start with the keynote talk, then it's going to quickly followed by the first talk. And just at the end, there's going to be a share Q&A. So for this, in case you have any question for the speakers, you can either just hop in during the Q&A and ask, or you can write your questions in the chat, specifying to which speaker the question is directed to, and then we can either read it aloud or you can read it aloud during the Q&A. Okay, having said this, I'm happy to lead the stage to Victor. So you can please share your slide, sorry.
Okay, great. Yeah. So thanks so much for the invitation. I'm happy to be here. Okay, so this talk now has a very vague title, Musings on the Linear Representation Hypothesis. And I'm going to do my best to clarify what I mean by this exactly. Okay, and so the line of work here actually encompasses a very large number of papers by many people, some of whom have been my very brilliant students and many of whom have nothing to do with me. But I'm going to particularly focus on this one paper, which is the geometry of categorical and hierarchical concepts in large language models, which in particular was really driven by my student Kehoe Park. So, all credit to Kehoe, all blame to Victor. Okay. Yeah, and so let me also just put a caveat on this, which is the amount of slides I have is utterly delusional for 30 minutes. And so I'm going to make no attempts to go through them and instead just try to maybe like highlight the aspects of this that I think are particularly conceptually interesting without actually getting through all of the content. So I apologize in advance, perhaps. Okay, so here's the big picture goal, or what I view as the big picture goal of this research direction, right? Which is what we're trying to do is develop something like a science of generative AI, right? A generative AI. So that is some kind of systematic understanding of how models actually work internally. Okay, and so what exactly do I mean by that? Well, it's a little bit hard to say, but I think we'll know it when we see it, right? But like as examples of things that we want, right? The goal here is to have a way of reasoning about a model's behavior in a manner that is like tractable, say analytically tractable, but still allows us to make predictions that are precise enough to actually be like useful for guiding, the design and control of these models, right? And so the inspiration here is sort of Newton's laws in classical mechanics, or a metaphor here is Newton's laws in classical mechanics, right? Which is clearly like just a imperfect description of reality, right? I mean, not merely because it was like, later replaced by other things, but also because like all actual physical systems that you deal with it in the real world are more complex than what is really captured by Newton's laws. But nevertheless, it's a thing which has sufficient predictive power that you can like genuinely do useful things with it. Right. Okay. So we're looking for like this kind of thing in the context of LLMs, right? Which is something that is mathematically precise, simple enough to be tractable, and actually useful. Okay. The ingredient which is like most missing at the moment, in my view, are abstractions, right? So like, what is the right way of thinking about LLMs, right? So there's a very low level thing, which is you can think about like parameters of the model, right? Or like the activation space. And then there's sort of like a very high level thing, which is you can view LLMs as like black box systems, which like eat prompts and spit out probability distributions over sentences, right? But there's something of a missing middle, right? In terms of like abstractions, in terms of like, like what is the right level to think about the things as an intermediate, and maybe an example of what I mean by this in the context of LLMs is there was, or maybe even is, a lot of excitement about the idea of circuits, right? These are like logical units of computation and transformer blocks, right? Which can be understood as like doing semantically distinct things, right? And my view is like circuits turned out to be the wrong abstraction in that they don't really describe LLMs well, but something on the level of abstraction of circuits would be satisfying as a way of reasoning over these systems. Okay, but we should understand what follows though in terms of in terms of this particular goal, right? And so what we're aiming for here is not just a particular like solution to an engineering problem. What we're aiming for here is something that is like a solid enough foundation that we can then like build a kind of comprehensive understanding on it, right? And so it's the first direction, or the first move in that direction. Okay, and so in terms of abstractions, a particularly promising direction is the so-called linear representation hypothesis, right? Which is the informal statement that high-level concepts that are semantically meaningful to humans, right, are somehow encoded linearly in the representation space of large language models. Okay, and so this idea has, had some like serious legs in the context of LLM interpretability, and it seems like extremely intriguing, right? And so some years ago, I set out to try and understand that, and there were some immediate questions. Okay, and so here are some questions that we would like answers to. First, what even is a high level concept, right? Like, what does it mean? There's like intuitively like, oh, the text is in English or the text is in French. This is about a man, this is about a woman, whatever, right? But like, how do you like mathematize that in a way that you could like build a theory on top of it? Second, what does it mean for a representation to be linear? And in fact, what even is a representation of a high level concept? Right. And then the third one is okay, like language is not just a bunch of concepts in isolation, right? There's a whole bunch of structure imposed by semantics, right? And so how does the semantic structure familiar to humans relate to the algebraic or geometric structure that is encoded in like representations in vector spaces, right? And so these are the things that we're trying to understand here. Okay, and so the starting point is what is a concept? Like, what is the sort of like abstraction or language that we could use to reason about these things? And the idea that we're going to go with here is to say, well, a concept is a thing that could, in principle, be intervened upon, right? And so what we're thinking of this here as like a language model is a generative model which takes in some prompt text and then generates some output, right? For the purposes of this slide, the output is just a single token, right? And concepts are latent variables in this generative process that you could change, right? So for example, a concept might be the concept of male versus female, right? Because we could intervene and change the output from male to female, right? Or it might be the English versus French, because we could intervene and change the concept from being English to French. Okay, and so this is just the abstraction that we're going to work with, but the usefulness of this is now we have gone from like a sort of fuzzy idea, right, as in like these are things semantically meaningful to humans, to a thing that has some kind of mathematization possible, right, via the formalization that we use for causality. Okay, so now we have a notion of concept that we can deal with, right, which are latent variables in a generative process that could be intervened upon in principle. Okay, so we need to make this a little bit more tractable, right? Operationalize it, right? So, if you're trying to build a thing which is like a scientific enterprise, right? What you need to do in particular is generate falsifiable hypotheses, right? So that you can actually test predictions, right? And so the first task is to say, all right, now I have an abstract notion of concept. How might I actually go about doing measurements on such things? Right? And so what we're going to do is focus now on two specialized forms of concepts, right? So the first is just binary indicators, right? So the concept of whether something is or whether an output does or does not have a particular property, right? So for example, and we call these binary features. So for example, we might have a feature, the is animal feature, where if that feature is active, then the output will be about an animal. Okay, and the advantage here is that we can, in a limited setting, like in the one generated token setting, identify this feature, right, with the set of all possible outputs that satisfy that feature, right? And so the point is this is just going to give us a connection between an abstract notion, right, the concept is animal, and something we can measure, right, which is the set of all words in the vocabulary that are animals, or that describe animals. Okay, another thing that we're going to look at, right, are simple binary contrasts, right? So these are concepts that have exactly two possible values. So examples of that are man or woman, right, or mammal or bird, right? And in the particular case where those two contrasts have exactly two natural and mutually exclusive values, right, then we're going to be able to identify that abstract notion with data by looking at counterfactual word pairs. By counterfactual word pairs, what I mean are things like the words man, woman, his, hers, king, queen, and so forth, right? Like words that differ on exactly one manipulable attribute. Okay, and so the point of this slide is really just like we're going from like an abstract mathematical notion to a thing that can in principle be measured with data, right? Or checked empirically. Okay, good. So now we have a notion of what a concept is, right? A mathematization of it, right? We have some sense of how it relates to things that we can measure, right? The next thing that we're interested in is the relationship between semantic structure and algebraic structure, right? And so the question is, what is semantic structure, right? And so there are two things that we found to be particularly promising in language. So one idea is causal separability, right, which is the notion that some concepts can be freely manipulated and some concepts can't, right? So an example of a concept that can be freely manipulated is I can often freely change whether the output is in English or in French, or whether the output is about a man or a woman, right? On the other hand, some concepts don't have this property. For example, whether or not the output is in English or in German, and whether or not the next word begins with a capital letter cannot be freely manipulated because English and German just have different rules about capitalization, just different conventions. Okay, the other kind of semantics that we're going to be interested in, which I'll gloss over just a little bit, is semantic hierarchy. There's a particular mathematization of this, but really the conceptually important point is that language contains notions like a corgi is a kind of dog, a dog is a kind of animal, an animal is a kind of entity, and so forth, right? And so somehow this sort of hierarchical semantics ought to be encoded in the geometry of the representation space. Okay, and so that gives us a notion of like what are concepts that what are concepts and what is the like semantic structure among concepts that we are interested in. Okay, and so with that set up, we can now talk about what are representations. Okay, and so right, so the two questions here are like, first, we need to give a sensible notion for what it means for a concept to be represented as a vector. Right, so large language models represent their inputs as vectors very naturally via the residual stream, right? But like an input is a chunk of text and not an abstract concept, right? And so the question is, how do you lift like representations of sentences or vector representations of sentences or vector representations of words to vector representations of concepts, right? And then the second question is, how does the semantic structure relate to the geometric structure of these vector representations? And I'll just mention in passing that we're going to make a totally unjustifiable, simplified mathematical assumption here, which is that if there is a natural geometry on this space, it can be represented by an inner product structure, right? And of course, like in full generality, what you'd want is just like a Riemannian manifold, and we're just going to like completely ignore that, work with an inner product because it's much simpler to present. Okay, and so almost all of the results that we're going to look at now relate to just the structure of the language model at the very final layer, right? And so you can actually forget about all of the transformer stuff, yada, yada, yada. Really what we're interested in here is the structure of the softmax link function, right? So when large language models are used to predict, to define a probability distribution over next words, I'm just assuming this is familiar to everybody now, right? The way that we do this is we assign each word in the vocabulary some unembedding vector, which we're going to call gamma. We use the LLM to map our input sentence to a vector in the same space. And then we define the probability distribution via the softmax distribution, which is an exponential, like take the probability to be proportional of the exponentiation of the dot product, right? And the thing that we are going to try to understand here is like, what is the geometry induced by this softmax distribution, right? That's really the object of study here. Okay, and so some background from previous paper that I won't really talk about, right? But the idea here is that given these binary contrast variables like man versus woman, there's a natural way of representing those as directions, right? And that natural way is just maybe the obvious thing that you would think, which is like take all of the vectors like man, king, uncle, whatever, take their average, and then take all of the vectors woman, queen, aunt, etc., take their average, and then just subtract the difference of those two things. And in a certain sense, it's a natural representation of a contrast, right? Similarly, there's a particularly natural inner product that is picked out somehow by the softmax. Again, I'm just going to gloss over what that is, right? And once we're working with an inner product, we can just choose a particular coordinate system where the geometry is Euclidean in that coordinate system. Okay, so upshot of this slide, there's already a way of representing contrast. There's already a particular natural inner product, and we're going to work in a coordinate system where we can just pretend everything is Euclidean. Okay. Yeah. Okay. So just in the interest of time, I'm going to move past this. Although certainly one could spend a month of their life just meditating on this slide, which I have. Okay. Good. So what does it mean to represent a concept as a vector, right? So that's sort of the core question that we're asking, right? And so what we're trying to give is a definition, right? A thing which is mathematically precise, right? But which captures like the sort of core idea of what we want, right? And so the particular version that we're going to do is this, right? Which is simply to say that a vector, which we're going to call L bar W, is a representation of a concept W if two things hold. One is if we take the representation of some sentence, and then we add L bar W to it, that should increase the probability that the output has the property that is represented. Right? So if this is representing the is animal concept, right? And then we add a bunch of this is animal vector onto the vector representation of a sentence, that should increase the probability that the output is about an animal, right? That's all that's being encoded in this first sentence. The second idea, right, is that if we add on this is animal direction, right, adding that on should not change any causally separable concept, right? So if I make the output more likely to be about an animal, that should not change what language the output is in, right? And so that's what's being captured here, right? This just says that the probability that the output is in French, say, right, is invariant to adding on adding on this representation of animal, right? And so these two properties seem kind of unambiguously necessary for it to be sensible to say that L bar W is a representation of W. Okay. Okay, I'm actually going to skip that. I skip both of those things. Okay, so I said earlier, right, that there's already an established notion, or there's already a fairly intuitive way of representing binary contrasts as directions. Okay, because you can just take like these counterfactual pairs and take the average of the differences of the vector representations of the counterfactual pairs. Okay, now the thing is, directions do not really have a notion of magnitude, right? They're just representing like separating planes in the space, right? But vectors do. Vectors do have a notion of magnitude, right? And moving from directions to vectors is actually critical mathematically, right? Because we want to understand the nature of compositionality here, right? And so we want to be able to do operations like adding like animal to dog, right? Things like this, like taking summations, right? Which requires us to have actual vector structure, and thus in particular requires us to be able to assign a notion of magnitude to the representations of various concepts. Okay, and so the way that we're going to do that here is the following theorem, right? Which I'm going to dwell on a little bit with my remaining time, which says that if I have a linear representation of some binary feature, right? So at this point, it's just a direction, not necessarily like with some arbitrary notion of magnitude, right? But so this is representing the concept of animal, right? Then there is some value, some scalar b sub w, such that the inner product, or the dot product rather, between this representation vector of my concept is animal, right, and the unembedding representation of any given word is either this constant value if the word is an animal, or is 0 if the word is not an animal, right? That is to say that for every possible output, right, there are only two values that this dot product can take on, right? Yeah, so I mean, that is the statement, right? And so this is saying we have, well, whatever, like hundreds of thousands of possible outputs and exactly two values that this dot product could be evaluated at, right? Where if the word is an animal like dog or chien or cat or whatever, be exactly. Are we simply write the log probability ratio that the output is dog versus cat, right? As we add on some multiple of this animal direction. Okay, and so the thing is, as we increase the probability that the output is about an animal, that should not change the relative probability, right, that the output is about a cat or a dog, right? The reason being cats and dogs are both animals, right? Now, we can write this probability ratio explicitly using the softmax distribution, right, to get the following formula, right? And so we know that the invariance requirement, right, is that this right-hand side should be free of alpha. Okay? But the only way to make this right-hand side free of alpha, right, that is unchanging as we enforce that the probability of animals increasing, the only way to achieve that, right, is for this inner product, or this dot product rather, L bar transpose animal G dog, to be exactly equal to L bar transpose animal G cat. Right, and so it's simply the fact that like this probability ratio is unchanged, right? This ends up enforcing this extremely strong geometric constraint on how the representations can look, right? Which is that there are only two possible values, right, that the dot product can take. Okay, and actually more or less everything just follows from this or from a very similar form of reasoning. Okay, and so I have what, like 5 minutes left?
Yep.
Okay, perfect. Great. Okay. And so the point is, once we have this idea, right, that there are only two possible values that can be taken on here, there's now a natural way of assigning a notion of magnitude to this vector, right, we simply take the magnitude of this, we simply take the magnitude of this representation to be this value B sub W, right? Like the point is there is a unique way of assigning a notion of scalar size to the representation of a concept, right? That's the thing that we are getting out of this. Okay, and okay, so what's being shown here is take the Gemma 2 vocabulary, right? Take all words in the vocabulary that are fish, mammals, birds, etc., right? And now each of the vertices of this polytope, right, is and I unfortunately won't have time to say how, but like we estimate the vector representation of these concepts in some fashion, right? And the theoretical prediction here, right, is that basically all of these vectors, say all of the mammals, should have basically the same magnitude when projected onto this space. Okay, and of course this is like a little imperfect. These are learned things, right? But what we do see is, in fact, there's a very tight clustering of all words representing these like sort of semantically similar concepts. Okay, and so I realized that like moving at the speed is probably like a little difficult to parse, right? But the point is like it is actually relatively straightforward to empirically verify that this like extremely strong mathematical property is in fact satisfied by the final layer representations of large language models. Okay, okay, so now there are a bunch of similar results connecting semantic structure to geometric structure. The way that these theorems all work is basically very similar to the result that we just saw, right? Which says more or less if two things can be freely manipulated in the structure of language, right, then that free manipulation has to be representable in the softmax distribution. And so if you just write out the softmax distribution, right, writing a suitable ratio of log probabilities, right, in very similar to the argument that we just saw, you end up getting some sets of orthogonality requirements, right? That's just how all of these arguments go, right? And so it's sort of like freely variable in semantic structure ends up corresponding to orthogonality of vector representations in a certain sense. Okay, and so here's a particular illustration of this in the context of hierarchical semantics, right? Where the way that we should read this is if the concept of, let's say, Z is dog versus cat, right, is subordinate to the concept of is animal, right? So I can freely change whether something is a dog or a cat from whether or not it is an animal, right? Then we need to satisfy this particular orthogonality relationship, right, which says the representation of animal is orthogonal to dog versus cat minus animal, right? Or just also is dog versus animal. Okay, and so the yeah, okay, and so right, the structure of that you can also see via these Gemma 2 embeddings, right? And so what we're seeing here is a projection of the Gemma vocabulary, right, onto the space spanned by the animal direction and the mammal direction, right? And what we can see is that the vectors for animal and mammal are not orthogonal, right? I mean, of course, right? Because if things are animals or mammals, those are not freely variable, right? But if we do mammal minus animal, right, that is this direction. So mammal minus animal is this vertical direction. Actually, I don't know if you can see in my mouse, but if not, hopefully that's clear. What we can see in this figure is that indeed this orthogonality representing the hierarchical semantics does in fact hold. Okay, and so again, like the upshot here is that you can just start off with this like very simple desiderata of like you need to respect which things could be semantically varied, right? And then using the softmax distribution, use that to derive like fairly strong geometric constraints about how the vector representations must look, right? And then you can go and check empirically that those constraints actually hold, and in fact you see that they do. Okay, and so then the overall structure that we get out for semantics and language models looks something like this, right? So if I want to represent a fairly complicated concept, like the concept of the output is about an elephant, right? This can be understood as being hierarchically structured. So we have an organism, which is an animal, which is a mammal, which is an elephant, right? And then the overall vector space representation of this thing is now represented as a direct sum of polytopes, right? So where each vertex of the polytope is like organism versus not organism, and then animal versus plant, and so forth, right? So it's just like this an obvious way of going from like vector representations of binary features to polytopes, which is just take the vertices of the polytope to be the vector representation of the binary indicator. Yeah, and so then the structure that we actually see in LLMs, the geometric structure, is this product of polytopes, or sorry, this direct sum of polytopes representing concepts, right? And then within this structure, we also have these orthogonality relationships corresponding to the semantics, right? So I mean, that's what this direct sum is relying on, that there's like this orthogonal decomposition. Yeah, and then yeah, just similarly, we see some empirical validation. Okay, and then I have another section on more thorough experimental validation. But in the interest of time, I think maybe I'll pause here, and I encourage you to look at the paper if you want to see how we did more comprehensive experimental evaluation of this stuff, which I think is interesting. Cool.
Thank you very much, Victor, for the talk. And now we can move to Luigi, and at the end we're gonna go through all the questions during the Q&A. So now we have Luigi Gresele from the University of Copenhagen, who's gonna talk about all or none identifiable linear properties of next token predictors in language modeling. And before we start, I also wanted to say that in this present also Emanuele Marconato, who's the first author of this paper, and he's gonna take in as well in the Q&A later.
Perfect. Can you? I hope you can hear me well.
Yes.
So thanks Marco for the introduction. And so yes, I'm going to talk about our work on identifiable linear properties of next token predictors in language modeling. And so yes, this is a joint work with Emanuele Marconato, with Sebastian Lachapelle, and with Sebastian Weichfeld, and we published it at AI Stats 2025. And yes, as Marco said, Emanuele is online, so he might join later for the Q&A and answer some questions. All right. So just very briefly, like again, what are we talking about? What are these linear properties? This is very related to the previous talk by Victor, so this helps. But to recapitulate, there's a lot of empirical evidence that syntactic and semantic relationships are expressed geometrically in the representations learned by these language models. And I think this is like became sort of well known probably after the famous Word2Vec paper. And here I took some figures from the Test of Time Award talk for that paper at ELLISxUniReps 2023, where there are classic examples such as this idea that the difference between the embedding vectors of king and queen and let's say hero and heroine are parallel, and similar relationships happen for the country to capital sort of connection. And there is one other linear property, which I'm going to talk about a little bit more later, which is this idea of linear probing, so that sentence embeddings are linearly separable. For example, by language, you can, in embedding space, linearly separate embedding of contexts which are in English versus Danish or other languages. And this enables what is called linear probing. And again, this is also very related to the previous talk by Victor. So what we are interested in specifically is the ubiquity of these properties, the fact that they're observed everywhere in a lot of these models. And we study specifically language models, which are trained for next token prediction. And so there's a fact which is kind of intuitive, but I'm also going to try to convince you of it later if that's not enough, which is that models with different internal representations can produce the same next token distribution. So there are many different representations that give you the same next token distribution. But we train the model just to essentially match the next token distribution of actual text on the internet. And so the question is, are these observed linear properties shared across all of the models which have the same next token distribution or not? And so we try to answer this. And the first step is we want to characterize the identifiability of these models, of these next token predictors. So, okay, let's start by defining what is a next token predictor. Again, Victor's talk helps me here because he already introduced them, but we have this finite dictionary of tokens, and then we consider there is the space, which is the space of all possible finite sequences of this token, which is basically the power set of this dictionary. And then the next token predictor consists of two functions. There is this function from the space of sequences to R to the D, which basically is we call the embeddings, maps sequences to the representation. And then there is another function which maps individual tokens to sort of R to the D, and this we call the unembeddings. And now what the next token predictor does is based on these two functions, it expresses the conditional distribution of the next token given the context. And this conditional distribution is essentially modeled as something proportional to an exponential of a dot product between these embeddings and unembeddings. All right, so these are the models we are interested in. What does identifiability mean? Identifiability is a statement of the kind, if we have two models with equal likelihoods, so equality of next token likelihoods, basically, this is equivalent to the fact that representations are equal up to this twiddle sign. So this twiddle sign, it is what we call an equivalence relation. So essentially it means any two representations will be equal up to a transformation, which is of a kind specified by this equivalence relation. And you can see this in the figure below. So here we have one next token distribution, and there are two different models, FG and F-twiddle, G-twiddle, that generate this same distribution. Actually, there's more than two in general. And there's a one-to-one correspondence between one distribution and a set of models which are all equal up to transformation in this defined by this equivalence relation twiddle. And this is what we want to characterize. We want to find what is the equivalent relation of next token predictors. And so we said that we have to start by looking at distribution and looking at how this distribution is parameterized by these models. And again, we said, so it's proportional to the dot product, or to the exponential of a dot product. So here in the figure, I showed some embeddings and unembeddings for a certain model with representation dimensionality 3. And so the embeddings are here on the top, and so there's this sort of red manifold. You can think of each point here as the embedding of a certain string of text. And below we have we centered the unembeddings in a certain way explained in the paper. And these G0 are centered unembeddings of individual tokens. So let's say Y1, Y2, and Y3 can be tokens. And here are these vectors corresponding to these centered unembeddings. Now, what I'm going to convince you of is that in general, this dot product may not be computed in the full representation space, but it may be computed in a subspace, essentially. So what I mean is the following. It can be, and we constructed a figure to show this, that if you take the original embeddings and unembeddings, and then you can project them onto some lower dimensional space. For example, here on the top, we start from the true embeddings on the left, and then we project them on the right through this projector P of calligraphic M. And similarly, we do for the unembeddings from left to right. In this case, the projector is just the identity. I will not define these projectors in the talk, but if you look at the paper, these are defined formally. And essentially, if you have the model, you can define based on the embedding and unembedding its projectors. And now the key point is the following, that the dot product between the original embeddings and unembeddings is in this case equal to the dot product between the projected ones. And so in a sense, there's only some subspaces that matter for this dot product, which is ultimately what matters for the next token distribution. And so based on these insights, we can try to visualize how the equivalence relation between next token predictors should be. And in particular, it could also be a relation between models with different representation dimensionality. And so this is what I'm showing you here on this slide. So on the left part of the slide, we have the model that we've already been looking at, which has a representation dimensionality of 3. And then we look at the projected spaces. And on the right side, we have a different model. This model has a representation dimensionality of 2, but then you can define its own projectors to sort of its subspaces where the dot product is computed, which in this case is essentially both identity. And then the idea is that within these projected subspaces, the two models are equal up to linear transformations. So when you project, they're linear up to certain linear transformation. They're equal up to linear transformations, which again we define formally in the paper. And so basically, this is this shows you visually like this equivalence linear. And the main theoretical result is a theorem that says if you have two next token predictors and they entail equal next token likelihoods, then this is equivalent to the fact that the two models are extended linearly equivalent Tweedle EL, which means essentially this equality up to a linear transformation in the projected subspaces. And this theorem, so this is characterizes the identifiability of these models, and it is a generalization of another previous result, which basically is a special case. If you have two models which have the same representation dimensionality, and they satisfy this diversity condition, then they're going to be equal up to a linear transformation everywhere, period. And to see that this is a generalization, you can basically see that if two models can be extended linearly equivalent without being linearly equivalent, a simple example of this is if they have different representation dimensionality, they cannot be linearly equivalent because the previous result was derived under the assumption of equal dimensionality of the models. So in a sense, our equivalence relation induces a coarser partitioning of the model space, and that is more general. Right, so now we started with this identifiability. Now we're going to talk about linear properties, and we redefine these linear properties in a way that we can study them with an identifiability sort of analysis. And we take inspiration from this work by Paccanaro and Hinton, which considers strings of text which can be decomposed in the following way. So they can be decomposed as the concatenation of three parts. There is a first part, which is the context or subject. Then there is a second part, which is the query or a relation. And the third part, which is a reply or object. And I'm going to give two examples of these. So the first one would be a sentence where you have a first part, which says, for example, all roads lead to Rome. This is a sentence, a string. And then there is a second string, which encodes a question. Is the text written in English? And this then is followed by something which is a reply to this, can be yes or no or whatever else. And the different one could be if you have first part, which is Miles Davis, so this is a subject, and then the second string, which is plays this is a relation, and the third string, which is trumpet, which is the object. So now the properties that we are interested in are relational linear properties, which involve geometric some geometric properties of how the context and query concatenated are embedded versus how the context on its own is embedded. And usually there are subset of tokens are involved. And I'm going to give an example of this in a second. But the idea is that based on this, we try to provide this relational formulation of a number of linear properties, starting from this linear relational embedding by Paccanaro and Hinton. And we also consider linear subspaces, linear steering, and linear probing, which have been considered in many previous work, including works by Victor and his collaborators. And I'm going to just talk about linear probing very briefly, where the intuition here is that the information which is contained in the embedding of the concatenated context and query, which is relevant to predict the next token or concatenated context and query, can be linearly read from the embedding of the context on its own. And I'm going to show you a picture of this. So we can have a query, which is the string corresponding to the question, is the text written in English? And then the idea is that one can linearly separate the embedding of those input contexts for which when you concatenate the context S with the string, the query string, they have yes as the likeliest next token from those which have no. So you can basically linearly read between these two possibilities, yes or no, just by the embedding of the context alone. Now I'm going to try to briefly go over identifiability of these linear properties, which we defined. And the picture looks a bit something like this. So we have a first model on the left part of the screen, which displays this relational linear probing, which we talked about. And as we said, each distribution corresponds to different models. So on the right part, we looked at a second model, and we see that these also have linear separability in the sense of the relational linear probing. So they both display the relational linear probing property. However, other linear properties may be disrupted. For example, these parallelograms in the model on the left side may be disrupted on the right side. And the idea is that, in general, these linear properties are shared across the extended linear equivalent models only within a subspace, because we saw how this extended linear equivalence class allows for distortions along directions which do not affect the dot product. There's an open question, which is, do we in practice observe properties which are not shared by all extended linear equivalent models? And if so, why? And I'm going to leave it at that, and I'm happy to talk about it more in the Q&A. With this, I'll conclude. So the question we wanted to answer is, are the observed linear properties shared across all models with the same next token distribution? And we answered this in 3 steps. We first characterize the identifiability of next token predictors. Then we have this sort of common framework for many linear properties. And then we study identifiability of the properties. So the focus is really identifiability of a property, whether it's shared, rather than just the structure of the representation. And our result is a proof that under certain conditions, suitable conditions, some properties hold for either all or none of these equivalent models that generate a given next token distribution. And yes, I'm going to stop here. Sorry, I think I went slightly over time. Happy to take questions during the Q&A.
Thank you very much, Luigi, for the talk. Thanks, box speaker. And now we can start with the Q&A. I already see some questions in the chat. I think these were directed to Victor. If the people that ask the question want to just opine, like, I don't know if Ricardo Cadei is still here around. If you want to ask directly.
Yes.
Okay.
I have a question to Victor, actually. More about how to interpret the causal relationship in his model. So, like in the beginning, he introduced also a DAG, and it's still not really clear to me like how to interpret it.
Yeah, so this is the DAG. Actually, maybe I'll just pull up the. Oh, 1 second. Maybe I close this tab actually. Okay, well let me not spend time looking for the slide. Okay, but I think you're referring to the DAG that is when we define what it means to have a semantically meaningful concept, right? We say, oh, there's a latent variable, and that latent variable could in principle be manipulated, right? Yeah, okay, good. So yeah, there is a little bit of a cheat here, right? But it's the same cheat that sort of powers all causal inference, right? Which is that whenever we draw a DAG in the context of causality, right, we are the variables in that DAG are some kind of like, like legible entity, right, which we assert is intervenable in the context of that problem, right? And somehow that's always false. Right, like whatever. Like classic examples are like you're doing like causal inference. You have a variable that says like, does this person smoke or not, right? But somehow like that's like abstracting away a lot of stuff that might actually be relevant for the underlying physical system, right? Like how many cigarettes, like at what time of day, yada yada yada, right? So I mean, this is like a classic problem of like abstractions in causal inference, right? Okay, and so thing that we're doing here is basically relying on this cheat, right? So we're saying, okay, look, I don't know exactly how to tell you like really what it means in like an ontological sense, right? Whether the output is in English or in French, but it's pretty easy in a like it when you see it kind of way, right? Similar to like, is someone a smoker or a non-smoker is a thing that you can like actually define, right? And the thing is like the mathematical formalism of causality, at least in like the Pearlian sense, right, sort of like starts with an ontology and then talks about relationships between it, right? And so the cheat that we are doing is just asserting that there exists an ontology, right, which can be represented as these latent variables, and then using that to sort of say, okay, now if we have these things and we have representations, what kind of properties do these representations have to satisfy, right? But there is sort of like a sort of like deeper philosophical problem, which might also potentially be a mathematical problem about like exactly what is it like, what does it mean when we like draw the variables like the nodes in causal DAGs. I don't know if that was like the question that you were worried
No,
about.
no, yeah, exactly. No, no, thank you very much for the answer. Obviously, like it's probably a much broader question and more philosophical, but yeah, I got your position.
Yeah. I mean, Frederick Eberhardt has a bunch of work on this question, which is very interesting to read. But it's somehow one of these directions that it feels incredibly like important for understanding what's really going on. But somehow it's actually also like not necessary to answer in order to like design experiments that could like falsify hypotheses.
I see, I see.
Thank you, Victor. Then we have another question in the chat from Dingley. I don't know if Dingley, you want to read it aloud or?
Yeah. I also have a question.
Oh, Dinling, I think you started off not muted and are now muted somehow.
I can't use Marco's laptop because we're in the same room, but can you hear me?
Yes, I can hear you.
Okay, yeah. Hi. I have a question about causal separability. I'm not sure if I 100% get it. So two contacts are causally separable. What does it mean? Does it mean they can be intervened separately? Does it mean I can imagine them as two nodes in the causal graph? Can you elaborate maybe on that?
Yeah, so this actually I think gets at the same cheating question, right? So yeah, it means that you could draw a causal graph where both variables are included as nodes in that graph. Right. So it's somehow a condition that, yeah, like, it is meaningful to talk about intervening on one and intervening on the other in a way that is separable, right? They are not like linked fundamentally by the underlying structural causal model, right? And so what yeah, I'm trying to think of like simple examples where this is like violated otherwise. Okay, maybe like from a previous paper, right? We were talking about biological sex and whether or not this was like an image generation, whether or not the output was a human or a deer, right? And somehow visually these things are not causally separable, right? Because male deers have antlers and humans never do. So this is maybe like too twee of an example, right? But the point is like it doesn't really make sense to draw it. Like if what you're interested in is like image generation, it doesn't make sense to draw a causal graph where you have like human versus deer and male versus female, right, as just totally distinct nodes in the graph, right? Because actually, like as you manipulate those things, actually, sorry, as I'm saying this, I'm realizing I don't really like this example. It's not very clear. Let's go with the one that's actually there, which is not that's actually in the paper, which is not perfect, right? But it's like English versus German, right? And capitalized versus uncapitalized, right? These are things that you cannot freely manipulate, right? Basically, because if the output is in German, right, then the rules for capitalization are just different rules, right? And so it doesn't make sense to have two separate nodes in the graph describing these things because it's actually like one of them is not merely causally influencing the other, but like deterministically constraining the other. But yeah, maybe the pithy answer is if like two variables are causally separable, if you could draw a causal graph where both of those variables are different nodes in the graph.
Okay, I see. Yeah, thank you.
Thank you. And if there are other questions, otherwise I have a question for Luigi and Emanuele in the meantime. So like your result, of course, concern models that have exactly the same output distribution. I wonder, like, from a more practical perspective, how much do you think this is true in the sense, like, if I take different language models, maybe also train on the same data, do I expect to have the same output distribution? Probably not everywhere. And I mean, this is also related to another work that I know that you're doing, in which you're trying to relax this kind of equivalence between log probabilities. I wonder if you had any thought on this. Or...
Yeah. Thanks for the question. Maybe I'll start answering, then Emanuele can add something to what I say. But essentially, yeah, you're saying right. So our work, as all identifiability works, starts from the premise that the two models give you the same likelihood. So you have to interpret what this means. It gives you a mathematical result, which is correct if the theorem is correct. Then the question is, what do you want to describe with this? And I think the temptation would be to say, well, that if you have two well-trained models on the same distribution, then they would both be equal up to a certain equivalence relation or share properties, as in the work we did with Emanuele. But as you said, like it might be that if you train two models, just if you change the seed, if you change something, they will not get exactly the same distribution, right? And strictly speaking, identifiability can tell you nothing about that. Can't tell you anything, because the starting point is the equality of likelihood. So you need some kind of robustness results to improve on that. But in the literature on non-linear or non-parametric sort of on let's say general non-linear models and representational learning, there's not a lot of this yet. There are some work by Simon Buchholz on this for a specific function class. But we have a more recent work with Emanuele and Andrea Dittadi and Beatrix Nielsen in Copenhagen, where we try to study the same model class, and we say, okay, what if you have two models which are close in distribution, and will they, their representation be similar in some sense? Well, so it's too long to basically give the full answer right now, but I'll just give the short answer, which maybe sounds sort of trivial, but the answer is it depends on how you define close in distribution. It depends on sort of the divergence between distribution that you use and how you define, obviously, sort of similarity of representations. But in the paper that we did with Beatrix, Emanuele, and Andrea, there is a very strong negative result for the Kullback-Leibler divergence, which basically says without any other additional assumptions, you can have models which are arbitrarily close in Kullback-Leibler divergence, and they may have, very non-linearly related representation. And so I think this is an open question. I think the question is like, what are, conditions which are realistic, which basically happen in models, such that you get this sort of robustness. And I think if you have that, if we get there, we can have something which is more, maybe more useful to describe empirical results, because then you can have two models which maybe, give similar next token distribution. And then you can say, well, maybe they sort of approximately share linear properties, but we are not there yet, but, maybe getting there. So and I don't know if anyone wants to add something to that, but.
Yeah, maybe one thing that I can add, that also another challenge is also confronting with the same tokens. It's something that really depends on the model that you use. So one thing that we faced was confronting models with different representation dimensionality. It's still open how to relate models that have different tokens. This happens when you use different tokenizer. So you may have different sources for modeling different condition distributions. the hope is that by working in this neighborhood, we may try to relate also linear properties to models that can differ under many aspects.
Okay. Thank you very much to both. Are there any other questions from the audience? Otherwise, I have maybe a final question for this. I think relates both speakers. I think both like all the results of all the paper of Victor, but also like the identifiability results that Luigi and Emanuele brought. They focus on basically the what happens in the almost in the output space, like the last layer of the model. I wonder if you consider so far if what the geometry of previous layers can tell you about, but like from the identifiability perspective, if you think, so this is more like for Emanuele and Luigi, if you think that there could be like identifiability result even like in previous layer, and both like for existence maybe of causal linear products for Victor in previous layers as well.
I don't know who goes first.
You're welcome to go first.
Okay, I'll go first. Okay, basically, I'll keep it very short. I think it's an excellent question. We have been thinking about it. I don't have any precise answer right now. I think it's generally an open question in the literature of identifiability of nonlinear models. For some specific architectures, you can probably do something. And there's previous works by ELLISxUniReps and Apo Hyvarinen on energy-based models and their identifiability, which have a proof technique which goes a little bit in that direction of sort of extending this result or back-propagating in a way this result through sort of the previous layers. But generally, I think it's still a very open thing, but interesting thing and should be done, I guess. Yes.
Yeah, so right, this has been like a significant question. Let me say like the difficulty, of course, is that as you move, or like the thing that is constrained by the language model, or the thing that is constrained by the data, right, is the probability distribution over next tokens, right? And as you move deeper into the model, like the relationship between the like internal representation and that probability distribution gets more and more obfuscated, right? In a way that, you know, I think sort of like naturally means that like we can't hope for such like strong, like mathematically precise results anymore, right? So the like skeptical view is like, yeah, as soon as you have even one transformer block in between the residual stream and the output distribution, things you know, are much harder. Like there's like just vastly more like freedom, and like there's no reason anymore, I think, to expect like simple linear representations. Now the optimistic view, right, is that empirically we know that a lot of this linear structure actually does exist on the internal layers, right? Like it is possible to do linear probing. You know, you can do things like train sparse autoencoders and so forth. And so there is something to be revealed there. I just think it probably will not be like as like analytically clean. You know, there is some sense in which like a relatively precise analytical understanding of the final layer is at least useful for understanding what will work at the intermediate layers. So for example, like this hierarchy paper I just talked about, we wrote a follow-up where we were trying to build sparse autoencoders that like intrinsically respect hierarchical semantics, right, by imposing some like suitable set of geometric constraints. And applying that sparse autoencoder, this modified architecture at the intermediate layers, still leads to excellent results, right? And so, you know, it is somehow like at least conceptual understanding from the final layer does push down to conceptual understanding of the intermediate layers. I'd also say that like there might be some hope based on the fact that the residual stream in the transformer is in fact just like a residual stream, right? So like even at the intermediate layers, there is a direct effect on the logit distribution, and results showing that early decoding can often work well. Yeah, and so yeah, I mean, I think that's kind of where it's at. Like mathematically, formally, I think it's hopeless, or like almost infinitely harder. But like conceptually, it seems to just work, right? And I think there might be some like intermediate approximation ground where we can like get some improvements on internal geometry as well.
Thank you very much. Okay, having said this, I want to thank again both speakers for coming here today for the beautiful talks. And before going away, I just wanted to share some info about the next appointment, just very quickly. So, sorry. So next appointment is going to take place on the 31st of July. We are going to have Bastien Rick and Florentin Gut. So having said this, thank you again to everybody and see you to the next appointment.
Thank you.
Bye-bye. Thank you.
Bye.